Okay, so I know we've been gone from class for a while. So what I'm going to be doing is we're going to be doing a review. Um, this review should help you get back into the swing of things where we were, because we had just started gas laws. Like I don't even think I'd finished the first video or presentation with you guys in class. So, all right. Anyways, here we go. We need to define what a gas is. So, when you ask yourself, what is a gas? Gas is matter which has no indefinite shape or volume. Gases will fill the volume of a container. So, when you're thinking about, barbecuing or grilling, you're actually using, if you're using a gas grill, it's got propane or butane in it. Um, and it's got it at a high pressure because there's a lot of it in there. Over time, even though you're using gas, the volume is still the volume of the container. It's just the pressure is going to go down. So these gas laws are going to help make sense of how gases interact in the real world. So let's write them down again. If you didn't write them down the first time, I highly suggest you do that. You're going to need to know how to use these to solve all the problems on your homework, your quizzes, and your test. So the first one we're going to go over is Boyle's Law. Boyle's Law is between pressure and volume, and it's directly proportional. And I'm going to explain what that means in a little bit when I individually go through each one. Now we have Charles' Law. Wow, can't spell today. So Charles's law is between temperature and volume. And wait, wow. This one is not directly, it's inversely. Sorry, I'm not feeling good today. And then this one is directly. Okay. Next one that we're going to go over is Avogadro's law. If you remember what he was famous for, it was the mole. So clearly his law is between moles and volume, and it's directly proportional. So I know in class we had some of you guys, we had started talking about Graham's law, but I decided it's not as used in Chem 1 in college or anything like that, so I'm not really going to expect you to go over it, so we're not going to go over Graham's law. But in place of it, we are going to go over Galax Law. This one is between pressure and temperature, and it's directly proportional. Okay, so we have another one, the ideal gas law. This one is just an equation. PV, so pressure times volume, equals moles times the gas constant times temperature. And then partial pressures. It's just kind of like a series in algebra. I think you guys do that. So you have PO plus P dot 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 plus PN. So each gas, if you have it in a container, like a mixed container, it's going to exert its own pressure based on its vapor pressure. Like there's actual calculations that go into this, and you can figure it out. But each gas is going to individually exert its own pressure within the mixture. Like they're not actually mixed. It's not a, like if you had a visualization of it, they're not like combined or mixing, but they're all sharing that space in the container, so they're all pushing out on the container. I'm going to show you a quick simulation detailing this so you can kind of understand what I'm talking about. let's see. There we go. So for partial pressures, just 'cause the actual mathematics of it is not hard at all. It's just you're going to be given partial pressures. I don't know if I'm even going to have you guys calculate all these yet because it's a little complicated. But you're going to be adding them up to get the total pressure. So I'm going to give you a visual representation of what gas looks like when you have it in a container. So let's see, I'll hold the volume constant. So let's pump some gas in there. And then we're going to pump in some red gas. It's smaller, so it's going to move faster. And then if you look up here, you'll see the more gas I'm pumping in there, the pressure goes up. What happens if I raise the temperature? Let's reduce it up a little bit. The pressure is going to go up slightly. The more temperature I add, the more the pressure goes up. The cooler I make it, pressure is going to go down. So that's how these gas laws are actually working when you have like an actual amount. Now, watch as I cool down these particles, they're going to slow down a little bit. As I heat them up, it's going to move a little faster. So I've posted a link to this simulation so you guys can play around with it in in Canvas. So see, if I put too much pressure in the container, that's what happens when you have like a bottle exploding or something like that. So the gas is just trying to go the path of least resistance, and then it's going to diffuse out into the atmosphere until it's as far away from all the other molecules as possible, so it can return to kind of its own little stable state. Okay, so you guys can play around with this when you want, but I just wanted to show you what I was talking about. It kind of helps see what I'm talking about if you can actually visualize it. Alright, so let's go and finish writing this table out. So P equals pressure, and that can be in torr, atmospheres, or millimeters mercury, but let's just say atmospheres for now. V equals volume. This is going to be in liters. N is equal to moles, as always. And then we have R. R is the unit, it's the gas constant. It's 0.0821 liters times atmospheres over moles times kelvins. So this is going to be used for you to cancel things out in the ideal gas law. And then we have temperature. That's usually going to be in kelvins. So let me okay. So let's go through and write down these gas laws. Let me see what I'm doing on time. Okay, not bad. All right, so Boyle's law. So Boyle's law states that the volume of a given gas is inversely proportional. So it's inversely proportional to its pressure if the temperature remains constant. That means it stays the same. So let me underline that. Stays the same. Okay, so what this looks like is you have V equals 1 over P. That's an inverse. Or you have P equals 1 over V. Also an inverse. So what this means is, I'm going to write this down over here. If your pressure goes up, your volume goes down. Your pressure goes down, that means your volume has gone up. That only applies with Boyle's law. That's what all of this is. Now, let's do Charles's law. Actually, let me do an example. That might help you guys. So let's just we'll do this one. Okay, so a gas has a volume of 460 milliliters at a pressure of 500 millimeters mercury. What will the volume be at 1.2 atmospheres? So right now this equation is telling me, or this problem is telling me we're going to have to convert. So you should know how to convert 460 milliliters to liters. So 1 liter times 1,000 milliliters. This cancels, and you're going to just move the decimal place. 1, 2, 3. 0.460 liters. So this is going to be equal to volume 1. All right. So pressure, I know we wrote this down. If not, the formula sheet will be online. So I suggest that you print that out. I worked kind of hard on that to make sure you guys had access to all the formulas you're going to need, and they're all labeled. Now, it has basic conversions like, gas conversions and stuff like that you'll need in temperature that I'm not expecting you to memorize, but like metric conversions, you're responsible for that. All right. So, anyways, back to this. We have 500 millimeters mercury. So you have the conversion factor for this is 1 atmosphere over 760 millimeters of mercury. So let me open the calculator just so we have that. So let's set this up. We have to convert the original value, 500, to atmospheres because that's what we're looking for. So this would be P1. So what we're going to do is 500 millimeters of mercury times 1 atmosphere over 760 millimeters mercury. And then that's equal to, I don't know off the top of my head, but probably about 0.7 something. Close. So your pressure 1 is going to be 0.65. We'll just do 658. 658 atmospheres. All right. So how you solve this, they're inversely proportional. So P1 V1 equals P2 V2. We have 3 values. 1, 2, and then we also have P2. P2 equals 1.2 atmospheres. That's up here. All right. So let's set this up. 0.658 ATM times 0.460 liters equals 1.2 atmospheres. And then you can put X, volume 2, whatever, just as long as you know what it is. I'm going to just put X to keep it simple. So X. I'm running out of space here, so let's move it over here. So pretty much all of this is going to be like basic algebra. So 1.2 atmospheres divided by 1.2 ATM. So to plug this into the calculator, what you're going to have to do is you're going to need parentheses first off. 0.658 times 0.460 divided by 1.2. And this is going to be equal to liters because these atmospheres right here cancel. So you're going to have X is equal to 2.252 liters or 0.25 or whatever. So V2 equals 0.252 liters. And that's how you would use Boyle's law to solve a gas equation. All right. That's only if the temperature remains constant, though. This won't work if the temperature's changing because then you're going to have to use a different equation. All right. So, next one is Charles's law. So Charles's law states that the volume of a given gas at constant pressure, that means it stays the same, is directly proportional to its temperature. Okay, so let's go over this. That means that V and T. So if your volume goes up, that means your temperature has gone up. If your temperature goes down, volume goes down. Very, very simple. So let's do an equation to kind of highlight this. Alright, we'll just do this one. Oh, and one more thing. I'm going to write down after I paste this in here why it's doing that. Okay, so T must be in kelvins. Has to be. Because there's some degrees Celsius and Fahrenheit that if you try to use this and it's a negative, it's going to give you like a negative number. It doesn't make sense. So it has to be in kelvins. If it asks you for what it'll be in Celsius, you're going to have to use the formula and convert it. But anyways, so how you set this up is, you have V1 over T1 equals V2 over T2. Basic algebra. So 4 liters equals V1. We have to convert 50 degrees Celsius to kelvins. So T1 equals 50 degrees Celsius plus 273.15. So that should be like 323 or something like that. You don't have to use the 0.15. That's just like the official one. You could just use 273 if that's easier. And then we have temperature 2 is 100 degrees Celsius plus 273.15. And then that's going to be equal to 373.15 kelvins. So we have 3 variables. Now we can set this equation up. So we have 4 liters over 323.15 kelvins equals X over 373.15 kelvins. So to solve this, we have to isolate X. Super easy to do. You can either cross multiply and divide, or you do it algebraically, because cross multiplication is not a real math function. So you would multiply 373.15 on both sides. Make sure the kelvin's in there. Okay, so that cancels that, or not that, but all right, it cancels the kelvins on there. So what we have is X is equal to volume 2, which is equal to 373.15 Kelvin times 4 liters, so we've already canceled the kelvins out, divided by 323.15. So all you gotta do is plug it in the calculator. So let's do that. So to do that, you need parentheses for the top again. 373.15 times 4 divided by 323.15. And then that means X is going to be equal to a volume of 4.62 liters. So V2 equals 4.62 liters. So as you see, the temperature went up a little bit. Volume also went up. Alright, so the next law we're going to go over is Avogadro's law. So Avogadro's law is simply the relationship between number of particles and volume of gas. So they are directly proportional. Okay, so that means that you have N and V. Number of moles goes up, volume goes up. Number of moles goes down, the volume also goes down. So, same way you set it up is V1 over N1 equals V2 over N2. So let me pick a problem out of here. Of course, this one doesn't have it. Let me just make one up. Say we have a balloon contains 0.313 moles of gas and has a volume of 2.46 liters. If an additional 0.214 moles of gas are added to the balloon, what is the final volume? Okay, so we've been given some information here that we have to plug into Avogadro's equation. So the way we do that, we have N1, it's right here. We have V1 right there. So we have N2 right there, but we have to add it to N1. So let's label everything. So that comes out to 72 equals 0.527 moles. So that's your second mole value, because it says if an additional moles of gas are added. And then we only have volume 1, which is 2.46 liters. So now you just plug it into the equation. If you are very good at using the equations, you'll be just fine on your exams for this unit. Equals, we don't know what volume 2 is, so we just write X over 0.527 mole. So again, you can cross multiply, doesn't matter, but I'm going to show you the way I do it. So I just multiply both sides by 0.57 or 527 moles. So times that, which will cancel that on that side and leave x alone, and you have 0.527 mole. So that cancels the moles out. So then we rearrange the equation to where x is alone and we're able to get a value for it. So 0.527 mole, actually we already canceled that, times 2.46 liters divided by 0.313, and then this will give you V2. So again, gonna need the calculator. Alright, so 0.527 times 2.46 in parentheses divided by 0.313. So your volume 2 is going to be equal to 4.14 liters. So let me see how I'm doing on time. Okay, so now we're going to go over Galax Law. I'm going to do a separate video for ideal gas law, because that one's a little trickier. Not really, but it's just different. So, Galax Law. This is new because we did not go over this in class. If the volume of a container is constant, meaning it stays the same, and the temperature increases, the pressure also increases. So that means that P and T are directly proportional. So, if you need a second to copy that down, take it. So that means when we have P and T, and then I'll do another one. So if P goes up, that means the temperature has gone up. The temperature goes down, the pressure goes down. That was like that simulation I was showing you. When I kept raising the temperature, the pressure kept going up. When I lowered the temperature, it went down. That's because the volume was constant. So, let's see. Oh, one more thing. Temperature, just like in Charles's law, must be in kelvins, or you'll get a wrong answer. Okay, so let's do an example from over here. It's kind of morbid. Here. No, we're not doing that one because I'm not converting from pounds. Alright, here we go. We'll do this one. Alright. Maybelline. Alright, we're just gonna go. So-and-so's backup oxygen tank reads 900 millimeters of mercury while on her boat, where the temperature is 27 degrees Celsius. When she dives down to the bottom of an unexplored methane lake on a recently discovered moon of Neptune, the temperature will drop down to negative 180 degrees Celsius. What will the pressure in her backup tank be at that temperature? So this is kind of a weird question, but we're going to, go with it and just pretend like we're on a moon on Neptune. So 900, first thing we have to do is let's convert this to atmospheres just so we have some practice doing it. You could actually leave it in millimeters of mercury and it would work fine. I'll show both variations of that. All right, so times 1 atmosphere over 760 millimeters of mercury. So that's going to be roughly like 1 point something, like 1.2, yeah, 1.18. And then we have temperatures that we have to convert to kelvins. So that's going to be 300 kelvins, I think. Yeah, 300 Kelvin, negative 183 plus 273 equals, I'm not doing. So that's 90 kelvins. It's really cold. All right. So the equation in itself is simple. We just have to, this is P1, T1, T2. We're trying to find pressure 2. So P1 over T1 equals P2 over T2. Because it's in a tank, the volume is held constant. So that means we have 1.18 atmospheres over 300 Kelvin equals P2 or X, whatever you want to call it, over 90 kelvins. So what I'm going to do is I'm going to multiply this by 90 kelvins to get P2 by itself. And then we're going to be solving for P2. So P2 equals 90 kelvins times 1.18 atmospheres divided by 300 kelvins. So your kelvins are going to cancel. So now you're in atmospheres. So all you got to do is plug this into the calculator and then you got your answer. So you have parentheses 90 times 1.18, close those, and then divided by 300. And then her tank's pressure has gone down to 0.354 atmospheres. Now I'll show you that you could do the same thing in millimeters of mercury. So we have 900 millimeters of mercury. We just still have to use kelvins. Equals X over 90 kelvins. So we multiply by 90 by 90. All right. So X is equal to 90 times 900 divided by 300. So we have 90 times 900 divided by 300. So you're going to have 270 millimeters of mercury. So I'm going to show you that these two are the same. 270 millimeters of mercury times 1 atmosphere over 760 millimeters of mercury. Let's move this over here. 270 times, well, actually just do 270 divided by 760. See, it's a little off just because of rounding and all that stuff, but it's the same thing. It's probably where I rounded it here. If I would have used the actual answer, it would have been the same thing. Do that. So we do and there you go. Same exact thing. So even if it's a little off, I'm not going to put questions on a quiz or test where you're going to get it wrong because it was off by like 0.001. That's ridiculous. But those were the 4 gas laws before the ideal gas law. I'm going to do another video specifically talking about the ideal gas law and partial pressures.